Okay, thank you very much for the invitation, and well, I'm happy to share with you a few remarks on how we can monitor forest changes from small scales to very large scales. And I don't know how many of you are familiar with forests, but I was kind of asked to give some background about the question. In Europe, we kind of love our forests because we pick mushrooms and they have like high cultural, also, climate mitigation value. And the EU has this goal to become carbon neutral by 2050. That means bringing down our industrial emission to zero. And they started to realize 3 years ago that, oh, that's going to be very difficult if you just cut down, mitigate the industrial sectors. So why not try to ask a little bit of help from the forest? Forests cover about 20% in Europe. And they set up a target based on what was the carbon sink at the time of having forest bring us the service of pumping, storing something like 400 million ton CO2 per year. This is a big number. It's like canceling the emissions of France and Netherlands. So why do we have an increase in carbon stocks, removal of CO2 from the atmosphere in European forest? In a nutshell, it's mainly a demographic region. It's not that much because forests enjoy climate change or whatsoever. It's because after World War II, many European countries had to cut forests to restart the economy. There were also before the war, like kind of over-harvesting, having very short rotation forests called coppice. And since then, forests have been replanted, regrowing. So they've been accumulating carbon because they take, of course, a long time to grow. And if you plant a forest in 1960, you still enjoy some growth today. At the same time, we were very lucky because not only the forests have been increasing in area and growing in carbon stocks, they still provide a significant economic output with more than 150 million tons of roundwood that have been extracted every year. So that's quite amazing because when we remove carbon, we should cancel the carbon sink. But in fact, the carbon sink means that the increment, as we say in forestry, the growth of the forest has been surpassing the removals that we take from harvest. So far, so good. However, came some kind of bad conditions for forest called extreme climate events. Those events, if they are like fires, they can kill trees immediately, of course. But they can also be more insidious. If you have a series of summer drought, the trees will grow less and less. And if the drought is very extreme, they can also die in the end. And we see a clear intensification, increasing frequency, acceleration of those climate events. The first noticeable one was in France and Switzerland in 2003. Then there was a super high heat wave in Russia in 2010. And now, almost every summer out of two, one region of Europe is experiencing, very high temperature or very strong water deficit. Because in Europe, when you have high temperature, it comes with drier conditions. This is an example in France, for instance. So you have on the left the kind of soil water deficit index and its distribution. And the black line at the bottom shows what were the conditions in 22. And you can see that it hits basically the minimum value, so the most severe deficit that have ever been observed during the entire summer. And of course, trees don't like it because not only it comes with dry conditions at the best time of the year when they can grow, they have a lot of leaf available. It also comes with elevated temperature. And sometimes the temperature itself can be a stress for plant growth. We observed, not talking about air temperature, but land surface temperature that were something like 50 degrees after some very strong heat waves in France. And at 50 degrees of leaf temperature, you can have a direct stress of temperature on photosynthesis. And unfortunately, even if we manage to stabilize the climate at 2 degrees, which is quite challenging, the challenge is not going to go away. You see here the summer temperature, instrumental record over France. In 23, we had this kind of one-off heat wave that should only happen every 150 years. But because we have this anthropogenic forcing of climate change, we experience again, only 30 years later, 20 years later, the same kind of average summer conditions. In a normal period, those kind of very hot summer, bad for plants, bad for crops, etc., should only happen, with a 3% return frequency. Today, they have more like a 10% return frequency at 2 degrees, which is very close from now, because of course, a global 2 degree means maybe 3.5 or 4 degrees first of France, because you have more warming in the high latitudes. They should happen something like 1 year out of 4. And what worries me even more is that if we don't manage to stabilize the climate, if we go for a global warming of 3 degrees, then we'll have some summer temperature like 25 or 26 degrees for which we have absolutely no analog. So we don't have any idea of what will happen during such hot summer because we don't have any analog in the past in France. We have to look for other regions. Now, how the forests have been doing, the classical tools to quantify the sink of forest, which is used for reporting to the climate conventions, is called inventories. It's like a poll for the elections. You decide upon a sample of some forest locations, you measure them, and because of the beauty of the square root of n, you get a statistical sample of the mean. And in fact, inventories are super powerful for estimating the mean carbon stock of a nation. With 10,000 plots, they claim an uncertainty of 2%. No way we can do something as good as that with remote sensing. However, they don't have any spatial ID, and they don't have a temporal ID because these inventory plots are only revisited every 5 to 10 years. So if you have a climate shock between year 1 and year 5, basically you measure the result when things have already happened. So you cannot really take action because you know what happened too late. Anyway, the inventories can be split into some kind of negative number, which is the carbon sink that we like, and some positive numbers that are the carbon sources. Europe has been on average a carbon sink, mainly because of the large green bars, which corresponds to the growth of established forests. So you have forests, they grow. There is a little bit contribution in a light green at the bottom of new forest. We don't have too much increase of forest area in Denmark or France, but in Southern Europe, like in Italy and Spain, there is a lot of former agricultural abandonment in the Alps. People were cultivating terraces very high in the mountain. Now these rural people have gone, so forests are kind of returning in those regions, but it's a small contribution. The point is that we decided upon an objective of 400 tons of CO2 per year, which seemed to be at hand, according to the sink in 2010. But since then, it has decreased by 20%, and this graph is not even up to date. Now the decrease is like more 30%. So if our target in 2030 is to do that, we have a problem, right? We have to break. So exposure to climate risk increased very strongly, and we have good evidence that tree mortality increased a lot, so this EU commitment is at risk. You would think that forests are changing slowly, right? Because one hot summer is not enough to kill all the trees, maybe 2, maybe 10. So you might expect that trees may have problem, but after 20 years of climate change, in fact, no. This is what happened in the Czech Republic. They were a carbon sink of 10 megatons of CO2 per year. And suddenly, bam, in 2019, they emit CO2 to the atmosphere. What happens? There was a very big drought. Probably you remember it here in 2018. The drought didn't kill too many trees, but the trees were weaker the year after in 2019. And then we had those insects called bark beetles. They like to eat spruce conifers. They basically exploded in population. And unlike many other insects which just remove the leaves, bark beetles are killing insects. They bore holes in the bark of the trees and the sap cannot flow upward. So the trees die basically because they cannot function anymore. And this massive killing of conifers in the Czech Republic shows that indeed forests can respond very quickly to indirect effect of climate change. Here we're talking about beetles. Of course, fires is also an obvious like nonlinear process by which if you have massive fires, you will lose in 1 year a lot of carbon. What about France? In France, the inventory people give us more than what is just requested from the climate reports. They separate the net carbon balance of forest in black between the gains in green. So most of the gains are from the growth of forest, which is measured by tree cores actually, not by diameter changes, don't ask me why. And then they also detect, every time they come back to a forest plot, how many trees have died? Like some trees, they were healthy the first visit, and then, they are yellow, they are fallen, they are eaten by insects, sometimes they are cut. So all the red bars indicate the carbon emissions, or at least the biomass loss, from trees that have died from natural causes. And the brown is the trees that we harvested. And you can see that the reason why the French carbon sink has dramatically decreased, almost by 50%, is not that much because we started to be hungry about wood and we started to take more wood out of the forest. It's because of this increase in the red dimension, which corresponds to climate-induced mortality, like drought, beetles, things like that. So typically, climate change is unfolding and it's causing a strong increase in mortality. And the problem, as I was saying, is that inventory were good when the system was in steady state to get a kind of national-wise budget, but they are really not good to understand natural mortality because natural mortality can happen at the scale of a cluster of trees. And then natural inventories, like you have an administrative unit, a small region, how many plots do they have? Maybe 30 plots. So it's like fishing fish in a lake. Sometimes you have a big fish, sometimes you have a small fish. You're not sure that you will sample how the system is actually disturbed. That's why we need maps, right? Of course, you're here in the room. If you bring together satellite imagery that have global coverage, all kind of nice properties, you can produce maps. And in fact, that's what we did. And I will show you a few examples. You can produce maps of everything in principle, forest type, forest carbon, risk, whatever you want. Before remote sensing, people were kind of old school. So you do a PhD, you understand very well the optical reflectance, you build a radiative transfer model, you try to invert the parameter of your model, you understand. You go from one forest to another, the parameters are not the same, you have to do another PhD and another one, and you spend your nice career like this. But of course, it's very time consuming. And then you have the LiDAR specialists, they don't talk to the optical specialists, they don't talk to the radar specialists. Now with AI, basically the hope is that you can explain to machine, okay, this is image, and I give you data and try to make map. It's very frustrating for the physical expert of remote sensing because we can do much better than what they did before, but we don't understand, right? So basically we have good maps that we don't completely understand. In terms of satellites, well, we have a deluge of data. So this is also a problem, is that you have apples, oranges, bananas. Some of them are long-term, like Landsat or MODIS, but generally they are relatively coarse resolution, and we understand intuitively that if you have lack of sharp images, you won't capture tree mortality at tree level. And you have, of course, those very high-resolution images. Some of them are commercial. However, satellites are all good for measuring things, but if somebody tells you I have a satellite to measure carbon, it's a lie. Huh? No satellite can measure carbon. Satellites measure colors, radar backscatter, LiDAR structural properties. So the art is to transform this information into something as close as possible to carbon. And one promising instrument for that is JEDI. I don't know how many of you know JEDI. It's like Star Trek. It's a laser that is sending beams from space and it's recuperating pulsed photons. So in the end, it got a return of energy, and the first photon gets returned back on the top of the trees, and you get what we call this waveform, which basically is the energy profile returned vertically. And because the LiDAR can penetrate relatively deep, in general, you have a ground return. So you can characterize tree height, and already from height, you have a better information on carbon. The only bad thing with JEDI is that it's infrared. So if it was green or red, you could see it at night. You could see the color beams of JEDI from your garden, but they are invisible because it's near infrared. So what we try to do, and JEDI is sparse labels. It's just like acupuncture. They make points, footprints. So it's like a gigantic forest inventory somehow. And what we did with Martin Schwartz, like more than 5 years ago now, we tried to teach computers how to do maps from the sparse JEDI labels. So it's a kind of regression problem. We put as an input Sentinel-1 and 2 images, and we tried to produce maps. We used a UNet model, nothing groundbreaking. 17 million weights. I dare to say that because nowadays you have models that have 500 billion words or so. So it's a small regression problem over France. Typically, you have 100 million of labels, 100 million of JEDI labels. You have about 500 million of Sentinel-1 and 2 pixels, and you can adjust your image with the UNet upon 17 million of kernels. So this is a forest in the north of France, Google Earth. This is how JEDI looks like. And for non-experts, I say, oh, if you are humans, you are going to take a pencil to do some kind of quigging with your brain. But since you're all machine learning people, you know that when you put spatial information, you can get a nice looking map. So basically, you can fill the gap intelligently of the JEDI footprint, and you can reveal that the forest had indeed very high value of height, like 30 meters. Some of them are very low. But now you recognize some patterns, like this forest in the middle is very old, it has some little roads, and some forests have been cut. The question is that you like the map, well, they're very beautiful, but of course you can have a lot of hallucinations with all things machine learning. So we produced a map over France, and at the time we started the PhD, we thought, oh, we have a good idea, but in fact, you know, other people also have good ideas. So at the same time, we saw the paper of Nicolas. He didn't use Sentinel-1, but only Sentinel-2 and JEDI. And then Potapov used the Landsat and JEDI with the random forest, so it's more simple architecture. And our colleagues from Denmark, they took it harder. They trained the model not on JEDI, but on airborne LiDAR, which are more accurate, and they use Planet very high resolution imagery to produce a map of height. So we had the opportunity to make a comparison over the same forest. Our product is on the left. The Planet product is just next to the left. The Lang product is here, and the Potapov product. And wow, visually they look different. Like the Potapov product is very flat. Lang looks like ours, but it's a little bit more, less sharp. And the Liu et al. Product is very sharp, but it's not as contrasted in terms of height dimension. And we could compare all those products upon some kind of judge, independent truth data, which are the airborne LiDAR data. And you can see that indeed this Potapov map, it has an R-square of 0.03. No point of making a map for having an R-square of 0.03. Over France, of course, maybe it's very good in other regions. The Lang map was not bad, but maybe because it didn't use Sentinel-1, we don't know. It has an R-square of 0.3. I would have expected intuitively the Planet map to be better because it's trained upon better data. But still, you know, it has more scatter and a bit of an underestimation compared to our map. So it's easy to say you have a good map because you work on France. Of course, the others are like global or European products. So it's a little bit unfair. Why do our results look better over France? Maybe a better deep learning model. Well, maybe because we use Sentinel-1 data, and that can make a difference because you have a lot of structural information compared to what Nico did, like using only Sentinel-2. Maybe because it's a local study, and you know, if you work hard over France, you'll get better results than if you do a global product and you don't check it over France. Then, more difficult problem, what is important for policymakers and forest practitioners, you give them a good map of biomass, they say, yeah, but you give them a map of biomass change, they can monitor things. And here it's a little bit more tricky because forests, they grow very slowly. Growth is a very diffuse signal. And when they are old, they hardly increase in height, they just increase in volume. So detecting changes is second order. It's much more difficult than detecting mean values. And you are vulnerable, your enemy in the business of detecting forest changes is phenology. Because 1 year, the tree is 30 meters and the color is yellow because it's a dry year. So your model learns with composite to make a map of 20 meters with yellow color. Another year, it's a wet year, it's green. The model say, oh, green, I'm going to say that the tree is 50 meters. Of course, it's wrong. So you have to vaccinate your deep learning model so that it can separate this phenological or drought-induced variability of the color, and it doesn't recognize it as a height signal. And we do that by sampling not annual composite, but sampling 10 days images. We train a lot of models, each time with 10 days images, it's kind of year agnostic. And then we do an inference, we do a lot of maps, and then we do the average. And somehow it vaccinates the model against the problem of variability. And you can see indeed that this product, compared to some ground truth, so you have an ALS, an airborne LiDAR, the difference in red shows the trees that have lost carbon. Indeed, this Sentinel model captures at least the big polygons of cut. And the good thing is that you can also stratify your data in a way that you would expect ecologically that the small trees, which are less than 5 meters, they have a big growth potential. So they should grow by 1 meter per year. But the trees that are 30 meters, they should grow by very little. So you can recreate by just reshuffling your pixels where you have growth signal for every pixel, what you would call like a growth curve per height classes. And our product is in blue, satellite data, pure satellite. And the kind of truth is in orange. It's not too bad indeed. The satellite can capture the kind of fine scale way, like young trees are growing faster and they have a kind of maximum growth rate at about 10-meter height. And then, of course, the growth decreases. And you can do that for different species. So you can see things that were, obvious, but also nice to see, like Douglas fir. In France, there are the major plantation species. They are like monsters. You plant them, and in 1 year, they grow by 2 meters. And indeed, what is good is that if you make a reference map of height in 2018, and then you show the difference of height for all the Douglas fir pixels in 2019, 2020, 21, 22, the curves are well organized. If they were noisy, they would go down, they would go up, and in fact, you can see that they go up and up. Poplar is also a fast-growing species, and of course, some larix or Aleppo pine, they are very slow-growing. Right. Now, thanks to the help of Jan Pauls and the University of Münster, the same kind of models with improvement in time have also been used to map canopy height change. We tried to do biomass, and that would be very interesting, over Europe and now also over the globe. I think Jan Pauls had a poster at this conference about this. And to answer the question, was our study better because it was only a French study? Now we have the kind of global map from Jan Pauls. And the answer is no, the global map, they are as sharp as the kind of French map for this French forest. So the reason why we had, let's say, better results than previous models is not because it was only a French study, because you do the same thing globally and the performances are the same. Right. So we did things over Spain. Every time we try to learn a little bit more. So in Spain, we compared against completely independent data, the national inventory data, and our prediction is on the y-axis. We compared the height of the forest with two models. One is trained with good airborne LiDAR data. The other is trained with JEDI. And you can see that indeed, good training data, from airborne, you get a little bit less scatter, but still the RMSE, is not too bad with JEDI. So the purpose here was to compare the kind of label quality. Then for Italy, we wanted to go deeper in time. So instead of using Sentinel, we use Landsat. Landsat is not the same quality of Sentinel. It has a lot of more problems. The color change is awful from 1 year to the next. So we built two models, an ALS-based one and JEDI-based one. And you can see the details of the forest. You can even see urban trees in Roma or in Milano, agroforestry trees. So it's nice because only with Sentinel, you get a good kind of sharp idea of where the trees are. And what we did new in the paper is that we had two models, and we had a few like national images, and we did what we call a Bayesian weighted average, a BMA, a Bayesian model average. We didn't have to choose which model should you take. Sometimes the ALS model is better in northern Italy, but the JEDI model is better in southern Italy. So we built a kind of consensus map by using basically Bayesian model averaging principles. Then we went over China. So China, it's a big country, bigger training, and you see the JEDI labels, they are very sparse. I mean, sometimes some years they are very good. They are very dense in some orbits. Sometimes you have gaps in some orbits. Yeah, it's pretty strange. And we wanted to have biomass. So the problem is to get labels. Is that people don't want to share the data. In Europe, it's terrible. In China, fortunately, we managed to have access to a lot of data, more than 50,000 UAV measurements of height and biomass, and 50,000 biomass plots. It's interesting because they didn't want to give us the data. So we were stuck to transform height to biomass. But we had an idea. We say, okay, we give you our height map. We give you a random forest snippet code. You keep your labels. You don't want to give them, fine. You train the random forest in your lab, you send us the weight, and then we produce the map. And that's a kind of middle way. It's not the one I prefer, but it's a way to still have basically access to data that are supposedly impossible to share. And what did we find in China? We find that, of course, most of the biomass is in the wet south of China. But you have a lot of interesting forest on top of the mountains, a lot of agroforestry trees in cropland and grassland. And as a matter of fact, when you stratify per province your biomass map, we found out that 19% of the tree biomass in China was not in official forest. It's in grassland, it's in cropland, it's in urban area. So this country has a lot of trees outside forest, which of course are important for carbon accounting. Right. Now, we know that there are problems with beetles and fires, and we want to monitor disturbances. I think most of you know what is a disturbance. It's a kind of extreme event that kills trees. And when you look at current disturbance product, well, you have the famous Landsat data. So everything pink should be a disturbed area. Then you have the European product by University of Munich. They have made a very fine job with Landsat data to recognize disturbance. Then you have some kind of operational alert product based on Sentinel-1. And when you compare the maps, well, they are very different. And of course, resolution matters. You have in the animation, like from 2 meter to 50 meter. At 50 meter, you lose a lot of information. So that motivated us to use very high resolution data to capture, we expect to see that. This is airborne LiDAR. Fortunately, they don't revisit many regions, but sometimes they do. So you have an image of a forest in the east of France, 2019-22, 2 regions. And you can see that with high resolution, 1 meter data, airborne LiDAR, these little red dots correspond to individual trees or cluster of trees that died. So we would like to do that with satellite. In particular, we want to see the small perturbations. So we developed models to exploit spot 6 and 7 data. It's images at 1.5 meter resolution, and they cover the last 13 years in France. And we trained this model, how to do height, with the airborne LiDAR data. We have also almost a full coverage over France. And we use a vision transformer. And the proof of concept was published in this paper by Feivel Vogel. And he also proposed a benchmark tool. So tiles that you can use for training, tiles that you can use for validation. And we give you all the data. So if you have a model, you can reproduce basically this benchmark. How do the results look like? So if they are good, they should look as close as possible to this ALS height map. In fact, our prediction is a bit more fuzzy, normal. It's 1.5 meter resolution. There was a 1 meter map by Tolan, which was surprisingly a bit more smooth. The planet map was also more smooth. And then when you enter into Sentinel or Landsat, the point is that you don't see individual trees because of the coarse resolution. So they look all green, and you cannot see the disturbances. In terms of bias, this open canopy product, so you can compare to some independent bias. As a function of height, you can see that our error is typically, let's say, less than 1 meter, except for very tall trees. Somehow slightly better than this Tolan high-resolution product, which was also based on high-resolution satellite. So now I will show you some examples. This is ground truth on the top, and this is how our spot history of height can match the ground truth. And you can see, well, of course, the value of high-resolution data is that you see now individual trees dying in forest or cluster of trees, which is pretty nice. They look very similar. Let's zoom at some regions. So you have the airborne LiDAR image in 2019 and in 2022. A lot of things happen because all the green areas are some kind of polygons where the trees have died. So it's a region where you have a lot of mortality. And this is how it looks in our map. So first of all, it's not as sharp because it's 1.5 meter, it's not 10 centimeter. But still, we have some blue polygons from the satellite data, which are matching quite well. The green polygon, they correspond to the true value. So high resolution data bring a lot of accurate information. And if you do another visual comparison here, they also capture the cascade of small disturbances. Let's compare with other data sets. So if everything is good, everything should look like the right-hand curve. With spot data, we get this. With the previous model that I showed you, the one trained with Sentinel-1 and 2 and temporal images, you get the blue pattern. So it's not too bad, but you miss all the small events. Similar model trained by Jan Pors. It's also good, but it's even better than the forms T, but you still miss a lot of events. And then this is the reference Landsat, the Global Forest Watch. They would see only this small polygon. The reference European data, the EFDA from Cornelius Senf with Landsat, it would also completely miss, maybe 70% of the real mortality events. And the operational data is also another solution. Another example here, you have a large disturbance, probably some beetles attacks. They are very sharp in the high resolution data. They are somehow in the right place, but very smooth, overestimated in the middle resolution data. And when you use Landsat, sometimes you miss 50% of them. And you have here some statistics like precision and recall, and classified per patches, per size of disturbance, right? And you can see that the 1 hectare disturbance, even if you want to focus on big ones, high resolution still improves things. So it's not just that we reveal the small disturbance, but we get better for the big ones because we get the shapes and the patterns of the big disturbance. How much time do I have? 5 minutes still? Okay. So we did that for other regions, Amazon, Africa, Southeast Asia, and I can show some results for Africa, the dense African forest. We know very little about them. So we created this kind of temporal model with annual height changes, and we paid the time to work with site PIs to collect more than 500 biomass inventories to transform our height into biomass. You can see our performance for biomass. So biomass of tropical forest is super difficult because it's very high. JEDI, you have 100 million labels in France, but because of all the bad data, the forests are too dense, they have no ground return. You have something like 40 million of JEDI labels in the entire Africa. It's much bigger than France, so label scarcity. And you can imagine that the number of Sentinel-2 clear sky image you get in Gabon, where you have 300 days of clouds per year, is very little. So basically, the quality of the input data is also super different from what you get in sunny areas. That makes it challenging, but overall, we get a certain R square. And if you compare that, for instance, with the ESA CCI map, they get an R square of 0.06. Again, they don't have the capability to predict biomass gradients against independent plot data. So the maps look nice, but in the end, what you expect from a map is to have an R square, which is significantly higher than 0.06. Then we look at height changes in Africa. You have on the right the regions where forests have been losing height, according to our results, and in blue, where forests have been gaining height. And you can take small sample regions. The red, again, are height loss region. And we have another product, which is called TMF. It's a famous product by GRC. It surveys all the disturbances over 30 years from Landsat, classified into 3 categories, like degradation, it's a small drop of Landsat, and then recovery, deforestation, so they think you have a full forest loss, and then some land use, and then the forest can come back if there is a regrowth. And visually, yeah, the area where we see a loss of height correspond to the areas where there is a disturbance in TMF. In fact, when they see regrowth, we also see an increase of height. However, if you look at the distributions, so we have a lot of pixels at 10 meters, and some of them have a height loss of 30 meters. There are not too many. And some of them have a height loss of 10 meters. Some of them, more of them, it's always power laws in nature, have a height loss of 2 meters. So it follows the power law and our distribution in the black curve. And you can viciously compare the distribution of our small height disturbances with what is detected by Landsat. And you can see that for the big things, yeah, somehow we agree. But we see 65% more small height loss events than what is detected as degradation or deforestation by Landsat. And we see 100% more small height loss event than what is detected as small tree cover loss in the Global Forest Watch product. So this suggests that those products are coarsely underestimating the left-hand part of the distributions where you have many, many perturbations, but they are too small in size to be detected by the Landsat data. And of course, they have an impact on the carbon balance of this forest. You can stratify your height loss as a function of the patch size. So on the right, you have big clearings, deforestation larger than 10 to the 4 hectares. On the left, you have small clearings. And as expected, if you transform height into biomass, you see that for the large clearings, you have a much larger biomass loss per unit area than for the small clearings. But then what you want is not only the amount of biomass loss per area, but you want to make the convolution with the distribution of disturbance. Because if you have a lot of biomass loss for very big events, but very few big events, finally for the carbon budget of the country, it doesn't count too much. And we found that most of the net biomass change, convoluted by the area and the patch size of the disturbances, is mainly occurring in this region of deforestation patches, which are on the order of 1 hectare, at the limit of Landsat. Degradation, surprisingly, was a bit like the distribution was a bit centered about most of the biomass loss from degradation are from patches which are about 10 hectares. And some forests are regrowing. It's a very dynamic system. And you can see again that most of the regrowth, gain of biomass, they come from very small patches. So basically, you have small degradation events, the forest regrows, and if you don't have high resolution data, you are going to miss them. So then we can do some carbon budgets. So you can take the whole African dense forest area. What is lost by deforestation, a bit like in the Amazon, we did that also for the Amazon and Southeast Asia, I don't have time to show the results, is less than what is lost by degradation. So degradation in Africa is really the main problem causing carbon losses. Regrowth happens, but is not as strong as to compensate for deforestation. And the blue area are forests which are called other forests because according to the TMF dataset from Landsat, nothing should happen here. But because we have higher resolution data, we still see that in this other forest, you have some action. If you split that into protected area, so all the polygons, you have a very uneven outcome of forest conservation. Some protected area in DRC, they are losing a lot of biomass. If you zoom around them, it's because you have people living on the edge of the areas, so they basically encroach deforestation into those protected areas, and they are losing carbon. At the bottom, you have forest concessions, and a lot of companies are basically paying countries to do sustainable forestry, so they should remove just the right amount of trees without damaging forest, not too often in time, and we found that we would expect concessions to gain carbon because after harvest removal, they should grow, but in fact, most of them were losing carbon, and the total loss of carbon from forest concession in Africa was larger than the one of protected area. And then we can also support national inventories because countries are using very, very simple models. And for them, it's a big stake because they can make a lot of money if they have good data. The problem is that right now, they use an IPCC book. They look what should be the growth rate of a tropical forest. They multiply the growth rate by their area. And then they have some Landsat data to get the deforestation with some emission factor. So their country report is two numbers, deforestation losses with very simple data, and carbon gains with a fixed growth rate. Of course, we know forests don't have a especially uniform growth rates. And we did a comparison here for all the African countries between what they report and what we think happens from the biomass change. And well, we found that some countries seem to slightly underestimate the carbon loss, and we can split that into gains and loss. So we found that generally speaking, we were within 50% of the report, but the countries tended to overestimate the carbon gain with this fixed growth rate approach, and also to sometimes underreport the carbon loss, probably because of lack of adequate data. 1 minute, just to show some work of Ibrahim Fayyad. He built what is called foundation model. I think most of you know what it is. Instead of trying to build the problem as a regression, like you need a lot of labels, we have to admit that in some problems, like biomass, if you want to make a biomass map directly from biomass samples, you have very few samples. Or if you want to make a map of species, you have very few samples. So you have to design other models, and he built basically a big contrastive non-supervised model that transforms Sentinel-1 and 2 data, a bit like the Google Alpha Earth embeddings, into embeddings. Then it classifies the embeddings without any supervision. And then with either zero shot or very small reconstruction model as a decoder, it can reproduce anything you want. Like you want a map of canopy cover. This model is called Dunia. And we compare this with some baseline models. You have two versions, zero shot and a small reconstruction. And you can see that this foundational model, which is unsupervised in the beginning, can reproduce, like here, it's a map of canopy cover, which is the same quality than specialized regression models. With the same model, you want to have a map of height, like what I showed before. It does it quite well. You want a map of crop types or land cover, it does it quite well. Very good. And even better, if we want biomass, we don't want the top height. I mean, we've been doing RH 98, RH 100, the top of the canopy, because radar and optical data, they see the top of the canopy. If you try to make a regression between the LiDAR height below the canopy and the Sentinel data that only see above the canopy, it's very difficult. We tried to regress RH50, RH25, maybe we don't have the right tools, but the performances are very bad. However, if you use this foundation model, you can reconstruct directly JEDI waveforms. You transform the waveform to embeddings, you contrast the embeddings with your pre-made embeddings, and then you rebuild the waveforms, either in zero shot or with a short generative model. And you have different examples of waveforms, and it's amazing how this foundational model can reproduce the waveforms. This is a very nice step forward, because if we have waveforms as a map, we will be very good for fuel load, for fires, for biomass. Getting the waveform, then getting the biomass is much easier than just the top height. Why does it work? Honestly, I don't know the magic. But at least my kind of natural science expertise tells me that it's because in nature, if you look at the JEDI waveform, you have only a finite way to organize things. Some forests have a thick canopy, some forests have a single layer at the top, single layer at the bottom, but you have only a finite number of, let's say, orthogonal ways to organize the waveform. And that's why your contrastive model can match them like a lookup table. If you have an infinite way for forest canopies to organize from the top to the bottom, this waveform reconstruction, I guess, should be almost impossible. So the way it is possible is not because of the black box beauty of AI, it's because of the beauty of nature that has only a finite kind of optimized way to organize itself. Yeah. So thank you for your attention, and I'm very happy to have questions from you.